Sujati with Saratech. Welcome to Simcenter 3D presentation. I'm your host, Ahmad Sujati. I am co-presenting this with Dan Nato, our application engineer and CAE expert. Today, we'll do a brief introduction of who we are. We will introduce a little bit of Saratech to you, but we'll dive into Siemens Simcenter 3D, and then Dan will actually do a demo for you. If there are any questions during the presentation, please type them in a chat box in your GoToWebinar control panel at any time during the presentation. We will respond to that at the end of the presentation, and we really value your feedback. Also, there will be a very short survey at the end of this seminar. If you would take that, we really appreciate it. We want to make sure that we're helping you, and this was a valuable tool. We know you're busy, and for you to take the time and to join this presentation, we hope that it brings value to you and your team. So just to share with you, Saratech has been here for 15 years. We help customers and companies solve their product development and business challenges. We're here to optimize your engineering investments. We help with design, analysis, manufacturing, and quality systems. We're the industry leader in the PLM space. With our partner Siemens, we're actually the #1 Siemens channel partner in Americas. We're based out of Orange County, California, but our team is across the U.S. We have 50+ employees across the U.S. who are close to our customers, who work with our customers day in, day out. I am based in California. Dan is close to Philadelphia, so you got both East Coast and West Coast on this conference call today. Next slide, please, Dan. So we're talking about Simcenter today, and the reason we're talking about Simcenter today is that there are issues with CAE and CAE departments today. There are issues that Simcenter will help with and solve, and problems that can be addressed, and efficiencies that can be gained out of Simcenter. A lot of the challenges that we have with the 3D CAE system has to do with the fact that the tools are disconnected. They are domain-specific. Each type of a simulation domain, whether it's structural, thermal, flow, each has its own pre- and post-processor and solver. So the tools are not integrated. They have, you have to have redundant work to achieve results that are across multi-disciplines. The other challenge with the CAE tools that we have today are that they're too time-consuming. You know, too often the simulation is done after the fact, and simply you are verifying a final design. You're not really involved with the design at the beginning. It's just a verification tool. The goal of this tool, Simcenter, is not to have a verification tool, but a tool that can predict time after time. Also, because the simulation process is too slow, simulations typically don't keep pace with design process. So even ambitious companies that try to use simulation as a mean to give input to design decisions struggle because of the time-consuming, complex, and issues that are making simulation obsolete by the time the design is complete. Also, there's very little visibility across some organizations to the CAE tools and what the CAE folks do. Again, traditional CAE teams and tools lack the means to efficiently communicate critical results of their investigation to the appropriate decision makers, which means valid design suggestions that could improve product performance go unnoticed, or they're noticed too late in the development process. And obviously, the cost impact is huge. The last item that I wanted to talk about on this slide are the fact that simulation teams face budget, staffing, and tool constraints that impede efficiency. Team members are typically siloed based on their simulation domain or familiarity with the tools that they're used to. For example, if you're a stress guy, you are not going to be on the thermal side, or vice versa. So it's nearly impossible for team members to help pitch to each other or help with each other's simulations when the workload spikes in one area or the lack of work in another area. Next slide, please, Dan. So what is Simcenter 3D and what does Simcenter 3D do for your organization? It's one of the best in-class simulation modeling, but it's an integration tool as well. And I get into each one of these line items in more specific. But you have an open system where you can work and do your pre and post processing. You can use multidiscipline physics, and you actually achieve best-in-class simulation modeling. So what that means as the 5 keys are highlighted here, Simcenter is a desktop tool which integrates in your environment as a pre and post processor. Within this environment, Simcenter offers best-in-class geometry editing tools, and Dan will talk a little bit about that today. It allows for comprehensive meshing within the tool and the unique ability to associate analysis model to design data. This helps us engineers to speed up our modeling process, and it helps us keep analysis models in sync with our latest designs. That means faster design for everybody, better iterations for everyone. Simcenter 3D also delivers accurate multidiscipline simulations from one centralized engineering desktop. So whether you are doing thermal, whether you're doing flow, or whether you're doing stress, that's all done within the same environment. Simcenter's 3D simulation solvers help you predict real-world performance, of course. Next, Simcenter 3D's unified environment is scalable, and it's extensive. It means you're familiar with just one tool, one interface, but you can expand, whether you expand in different disciplines or whether you expand in your geometry, it can all be done in the same tool. It can be automated, and routines can be written in this environment. Next, Simcenter 3D Engineering Desktop provides the tools for you to help create and communicate with broader organization within your enterprise. Finally, Simcenter 3D is a common interface for engineers and engineering departments to capture knowledge and leverage that knowledge across disciplines and across organization. So, with that said, and knowing that you have a tool that can help you integrate your data and your processes and your simulations into one location, let's dive into a little bit more of a Simcenter 3D Engineering Desktop. It's an integrated, again, an integration of common simulation environment. As an engineer, I do remember if I had to do thermal, I had to go to a different tool, create my own pre and post mesh or processes and mesh and do a thermal. Then I have to go to another tool to do my stress. This brings it all together in one platform. You get timely product insights, and you can give that feedback to your development teams much faster than before. Your simulation results are visible by the entire engineering organization, and they can make their decisions much earlier, and it's not just a final design verification at this point. You also are removing resource constraints to enable a more flexible and responsive simulation team. Next slide, please, Dan. So to summarize, before we get into Dan's demonstration, Simcenter allows you to improve your modeling predictions. Today, we will talk more specifically about CAD and CAE integration. We're also going to talk about Streamline collaboration. So if you have multiple folks working on a part, how that's all done in one desktop area. But also, I want to highlight that this is a multidisciplinary modeling tool, and it's designed and it's made to shorten the design cycle, which will lead to cost savings and efficiencies. With that, I'll turn over the presentation to Dan, who will walk you through a model here.
All right, thank you for the introduction and the background. So today I'm going to give a presentation using Simcenter 3D. So a little bit of background about myself. My name is Dan Nato. I'm an application engineer for Saratech. I'm located in the Reading, Pennsylvania area, and my expertise is in FEMAP, NXCAE, SimCenter, NXCAD, and also NXNastran. So here is just, sorry, there's a thunderstorm warning in my area. So this is a common question that comes up all the time is, hey, what is the file structure within NXCAE or SimCenter? And here you see it on the left. You'll see that we have our master part. So our master part is the model that comes from CAD. Normally this is the part that you're going to, send to machining or your final design. So inside our FEA world, we have an idealized part. So the idealized part is a representation of the master part. So with this idealized part, we can make changes, remove holes, fillets, rounds, make assumptions, do what-if scenarios with our part. And making these changes on the idealized part does not affect the master model. So if you are pulling this from a master level assembly, we're not actually editing the assembly, we're editing our own individual part. So from there we take our idealized part, we create our FEM model, so we define our materials properties, our mesh, and things like that. From there we move it into a simulation part. So the simulation part holds the information about the solver, our loads, our constraints, our boundary conditions, things like that. So you'll see up here in the top right some benefits. So we're working in one environment, so our CAD is made here in, NX, and our FEA model is also made here in NX. So now I'm just going to go through these pretty quickly. I want to get to the demonstration, but here's the master part. So the master part just is a straight up CAD part. So most of the times you're going to pull this from an assembly. If you're using Teamcenter, you're going to pull it from the top level. So, or if we're going to be talking about assemblies shortly. Now, one thing it says here is that an idealized part is not required, but we'll talk about why I like using an idealized part, and I recommend everybody has one. So, some of the nice things about the idealized part is these what-if scenarios. Maybe we want to remove holes, fillets, as you see in this one. Maybe we want to use some more things, do some mid-surfacing modeling and things like that. So we have the capabilities to edit our own individual idealized part without messing with the top-level assembly. So we're not physically editing the master part. So right here's a nice little picture. So maybe we want to remove those rounds. Maybe we want to remove some of those holes. Maybe we want to try and expand the hole. See, does this make a difference? Remove holes. Maybe we want to stiffen the plate or something like that. We can make these changes to the idealized part, and we aren't editing that master part. So now a couple things that we can do is defeature. Defeature is pretty straightforward. Remove holes, rounds, fillets, things like that. We can create mid-surface representation. A lot of times we're going to want to create mid-surfaces. So creating mid-surfaces is just going to help us get a nice representation of the model without driving element count up. So that's a common FEA procedure to be done. We can also use synchronous technology. So in this picture it shows a really nice thing. Hey, let's see what happens when we move this little stiffened region one distance or another. So we can check these idealized parts. We can do all these what-if scenarios or what-if cases. So even with our idealized part, we have full capability of the CAD program in the background. So we do have NX. So you can switch your application and go right and do the modeling. So whatever capabilities you have in modeling, you'll be able to do that with your idealized part. So if you need to, create some different surfaces, curves, and extrude, revolve, create patterns, things like that, you do have all those capabilities. So the idealized part is the key to not messing up the top level assembly and trying to do what if cases. So from there you're going to go ahead, set up your idealized part to what you want, then you're going to create a FEM part. So with the FEM part, you're going to go ahead and create your topology, so your mesh. So from here we're going to go ahead and mesh the part, make sure that we have the right materials and properties. And then after we have our FEM part, we're going to go ahead and create the sim part. So some of the, why we're creating the sim part is at this level we're going to go ahead and create our boundary conditions, which would be our loads and constraints. we're going to go ahead up and set up our solution. Hey, what do we want to run here? Do we want to run normal modes? You know, solution 101, 103 if you're using Nastran. Maybe you want to step up and use some thermal or flow solver. You would just go ahead and specify what solver. So as you can see right there, it's a nice spot to go ahead and pick what solution sequence you want to run, all within, you know, this one package. So what I want to spend my time today in demonstration is going over a assembly. So I want to do an FEA of an assembly. So the normal procedure would be you have, in my case, I have two master parts, and what you would do is you would combine them together based on, you know, how your assembly would be, and then you'd create one single finite element part where you would connect them together, you know, maybe with glued contact, have coincident nodes, rigid connections, things like that, and then you'd have one simulation part. But today I want to go over talking about the assembly FEM. So the assembly FEM is a little different of a concept, but each individual entity of the assembly has its own FEM part. And then we're going to have a top-level FEM part as well. So here in my image now, each master part has its own idealized part and its own FEM part. One of the nice things about this is that maybe some change is made. It's easy to, you know, branch this off because I already have individual FEM parts and I can move them between each assembly without having to adjust my top-level assembly. So each one's individualized. So from there, I have my assembly FEM, and then we would create a sim part, which would be the solution of those assembly FEM. So let me go ahead and show you this inside NX. I think it's easier to see as I demo it. All right, just wait for the screen to pop up. All right. So here is a part that I'm going to use. So this is, we'll just say I am an engineer and my job is to go ahead and create the finite element model of this part that is going on top. Well, it's going to connect to a satellite. So my job is to model this and connect this to another assembly that the rest of my coworkers are working on. So what I'm going to do here is I'm going to go ahead and start the application pre and post. So this is where we hop on into Simcenter from NX. So now this is how Simcenter Setup. We have a ribbon just like all of our NX things. Now we have a simulation navigator since I'm in the sim, and then I have a simulation file view so I can see what I'm looking at. So right now the solar panels is the top level name of my assembly, which is made out of these individual parts. So I have hinges and things like that. So what I want to do is I want to create an assembly FEM. So I'm going to right mouse button on this and I'm going to say new assembly FEM. And I'm going to leave it blank for now. And in my case, I'm going to use NX Nastran as the solver. All right, so now I have created an assembly FEM. And now we see our simulation navigator. My top level is the assembly FEM. And it's made out of solarpanels.part, which is the assembly. So these are all the parts of the assembly. So maybe, you know, somebody else created the CAD and it's my job to go from here. So I'm going to go ahead and take this inner and outer part and I'm going to go ahead and right mouse button. I'm going to say map a new one. So let me create right here a FEM model of this outer and inner part. So right now I'm going to go ahead and say I'm going to use NX Nastran and I'm going to call it solar panel FEM. Okay. So what I'm doing is I'm taking this CAD part and I'm going to create a FEM part. So right here I want to use all visible. I want to create my idealized part and I'm going to use NX Nastran structural analysis again. So now this part has been created into a FEM and I'm going to do the same thing with the outer as well. So I'm going to right mouse button, I'm going to say map new. Now the reason I'm saying map new is because I never created this finite element. If it already existed, maybe one of my coworkers did this already, it's easy for me to add their part into my assembly FEM because I can just hit, I'll just do this for example, map existing. I only have one other in this location, but I can go ahead and grab something somebody already did. So if it already existed, I could just go ahead and grab it. So this time I'll say map new. Like before, I'm going to use NX Nastran for my solution. And I'm going to accept all the defaults. So now if I look at my top level assembly FEM, it's just now the two solid parts that are brought in. I don't want to bring in the class and things like that. I'm going to use RBE2s to simulate this region. So I'm going to make a few changes to each of these parts. I'm going to do some geometry defeaturing. I'm going to do some mid-surfacing to get a nice quality mesh and good representation of this. So what I'm going to do is check into this outer part, and this time I'm going to step to the idealized part because I want to edit the idealized part, not the physical part. So I'm just going to double click on this and make it the displayed and work part. Now, one thing that NX CAE or Simcenter here is doing, it's saying I have to promote it. You have to go ahead and move it, the component to this level of assembly so I can edit it. It's just I guess a safety feature. Just make sure that you're doing what you think you are. So I'm going to go ahead and create this into a simple flat plate so that I can mid-surface it. So I'm going to use some synchronous technology really quick to move faces, and since I've done this before, I remember these values, so I'm going to move some of these faces up so that I get a nice clean part that I can go ahead and mid-surface it. I'm just going to go ahead and do this to both sides of the part. And then I'm going to repeat this same command with the other part when I'm done with this. So now that I've done the simple defeaturing of the model in this case, I'm going to go ahead and mid-surface the part. Now this is a very easy part to show a mid-surface, but there is a lot of complexity in the mid-surface creation. So for our case, it's very simple, gives me a progressive, but the mid-surface creation is very strong. So now, very easily, this part has been mid-surfaced, and I'm going to go ahead then step up to the next level and mesh it. But before I get there, let me go ahead and do the same procedure to the inner panel, the idealized part. So just like before, I would need to promote my part to go ahead and make this change. So I'm going to do the same command. I'm going to move a couple faces and get this nice and clean real quick. So a lot of the time as a FEA user, you're going to spend a decent amount of time cleaning up, geometry, making it look like, you would want it for your FEA model. So the ability inside NX, the synchronous technology, the full application of NX to go ahead and, create your own features and go back. If somebody else was using NX for the creation of the part, you have the full history that you can go back and just easily look at the model tree and just remove rounds and fillets that way instead of having to go back and remove using stuff like synchronous technology and some of the other idealized geometry features inside NX. So that's one of the really nice advantages of having it all integrated in one location. So I'm going to go ahead and mid-surface this one just like I mid-surfaced the other one. And now I'm going to go ahead and step back up to my top level assembly FEM here. So you see I have the same thing that I have, and both of these just need to be updated since I made changes to them. So just easy, I can just double click on it and it's going to go ahead and update that one, and I'm going to double click on the other one just to update them. And now if I step back up to my assembly FEM, you'll see that now this is how I idealize my part, and this is what it looks like. Okay. So now let me go ahead and step up to the inner part, and let's give it a quick mesh. So I'm going to throw a 2D mesh on this surface, element size of 40 millimeters will work. NX will give you an automatic collector. I like to create these on the fly or beforehand using this mesh collector button up here. So what the mesh collector is it tells what type of topology, it's 2D, 3D, 1D, and what type of physical properties. So right here is where I'm defining my properties. So I'm going to do a P shell, and my P shell is going to be made out of, in this case, I'm going to make it out of epoxy, and it has a thickness of 25 millimeters. So now when I mesh this with the size that I said, it's going to be made out of that epoxy, and it is going to have that thickness. Now I'm going to go step up to my other part, which was my outer, and I'm going to do the same thing. I'm going to throw a 2D mesh on this, and this time I'm not going to create a collector just to show you what would happen. So it throws down a mesh, And now it automatically created this collector for me, and I can go ahead and edit it and go ahead and make those changes. Now I need to make sure that I get, like before, I have the correct thickness for a mid-surface, and in this case I have the correct material, so I'm going to do this one also as an epoxy. So now when I step up to my assembly FEM level, now you'll see that both my parts are meshed and together. So what I want to do here is I want to represent that clasp that went in between. So one nice thing here at my assembly FEM level is just to create a 1D connection, which is just I'm going to RBE to one of these to the other. So it's going to be rigidly connected. So I'm just going to say these three nodes here are going to be connected to the three nodes opposite of it, which is going to give you an accurate representation of the solar panels clasps here if this would be rigidly connected and stiff. So you see we can get a nice representation of what's going on. So let me go ahead and save this. So file save. And let me just save this and let me put my name here so that I can find it. So my task has been completed to set up these panels to be added into the assembly finite element model that somebody else was working on. So let me go ahead and open the model where this needs to, and I'll say merge, where this needs to be combined with the other one. So I'm just going to go open, and in this case I'm going to go ahead and grab an assembly FEM that already exists, and this is going to go into this satellite. So this is just going to take a quick minute to load. It's pretty large. But we'll just say, you know, maybe our coworkers were working on this model while I was working on mine. And then we need to merge these two together. So if this is, you know, the top level assembly, if we look down here in my simulation file view in the bottom left corner, you see I have the top level of that assembly open, and there is a lot of entities inside that assembly. And then I also have my assembly loaded, which isn't needed to be loaded at this point, but I'll show you how we're going to bring mine into theirs. So you'll notice at the top level here is the satellite assembly FEM, is what we're looking at, but nested inside there are other assembly FEMs. So there is this telescope detector, which has other finite element models in it as well. So there's simple there's simple FEM models in here, and there's also assembly FEM. So you can nest inside your assembly FEM other assemblies. So what I want to do is load in right here. It says not loaded the assembly. So let me go ahead and load the assembly in. And you'll see these solar panels, which was my job to work on, are ignored at this point. They haven't been loaded. So I want to grab all these. I can hold down Control and do those tricks, but I'm just going to right click and say find all matching solar panels. And this time, I'm going to say map existing. Before we did map new because I was creating them, but these have already been created, so map existing. And I'm just going to go ahead and find the one that I did. So solar panels, assembly FEM, and I put my name there so I can find it. And you'll be able to see down here in the corner that this is the part that I was working on. So now when I hit OK, it's just going to throw those into the model, just like it was in the assembly. So this is where you can really leverage your CAD. Now for my case, I need to do a couple more things at this level. So what I want to do is connect my part to the rest of it. So using something just like we did before to represent that other class, we can just do a 1D connection, and I'll just specify from one side, and I'm going to go to the other. This might be hard to capture to see the RBE2 connection. But basically, I would connect that rigidly all the way around the structure. So if I did that at all four of my locations, it would be connected. Now it looks like I'm running a little bit low on time, so we'll just say that I created that RBE2 all the way around. What we would do now is our assembly FEM has been set up. We would just right click on our assembly FEM, and this is where we need to create our simulation. Now one thing that before I do this simulation, I seem to forget this a decent amount. At the assembly level, you can go to Assembly Label Manager, and this is an important thing, and this is one that I commonly forget and I get yelled at when I solve it, is that you see that I brought in these components and I have the same labeled nodes and elements as I do other entities in the model. So we want to make sure that we resolve some of these conflicts before we merge it in. So using a button simply as automatic resolve, it'll renumber our entities so that they do not go over. Now, you can change these as well to whatever you'd want. So if you need to block it in a certain region, you can go ahead and block it. So now let's go ahead and create this new simulation. And you'll see right here, I'm going to use NX-Nastran for my case. Specify whichever solver you'd want. It'll pop open the new simulation. And this is where we would define what type of solution. So I'm going to use solution 103. I'm going to find the eigenvalues. And if I need to change any parameters, maybe I want to find more modes. So here's Lanczos data. Go ahead and specify that I want to have 20 modes. I can go ahead and enter 20 modes, and then I'll solve for the first 20 modes. So if you needed to define, some more contact, maybe you want to put loads and constraints on the model. Since I'm doing a unconstrained model here, I could just go ahead and solve the solution if I didn't have any, free edges or anything like that. If my model is nice and clean. So now I'm at the point where I can go ahead and solve it. I already have it solved. It takes a little bit to solve, so I think it's easier to do the cookie cutter kitchen show here. So let me just go ahead and pop over another model that I have solved just to save ourselves some time. So here you can see the model has been connected rigidly all at each location all the way around. We're working with the sim level, and I went ahead and solved it. So now we can just go ahead and look at something like results. If you want to see, normal modes, results, I asked for the 20 modes. And the nice thing here is I can visually double check, and I see my first 6 modes are right around 0 hertz. So looks like I do have a nice clean model, and me interfering with my coworkers, we came out with nice results. So if you wanted to view more results, step through these as well, this is something that you could go through as well. So that's all I wanted to show with the demonstration. So now let me hop back over to the presentation. Looks like we're running low on time, so I want to make sure I get everything in. So basically what we went over today was the file structure of Simcenter. So you have your idealized part. Understand what your idealized part is. It's doing what-if scenarios, and you're not editing with the top-level CAD assembly. And then you have your FEM part, so where you're going to go ahead and define materials, properties, your mesh, things like that. And then you have a sim part where you're going to apply your loads and your constraints, and you're going to go ahead and set up your solution. Now, in our case, we went through an assembly FEM, which is the same concept, except you're breaking each individual part of your assembly into its own finite element model. So some of the nice reasons for doing these assembly FEMs is it's easy to reuse those little, I'll just say, parts in this situation. So if I needed to make some sort of change, or maybe one part has been drastically updated, it's easy for me to go ahead and make these changes. So you see right here, distribute work among our team. So like I showed in our example, somebody was working on a part of the satellite, somebody else was working on it, and we brought all our work together in one location to go ahead and create this full assembly finite element. Instead of one person working on the whole entity as one, now each person can work on them as pieces. So we can control each step of the way here. So not everybody's working on the assembly, each person's working on their individual entity, and this is a good way to collaborate and reuse existing stuff that we already have.
Dan, you actually answered one of the questions that was typed up. How can creating assembly FEM save you time? It's really the collaboration and the fact that multiple people can use the tool, correct?
Yeah, so the ability of creating these assembly FEMs is just so that we can collaborate, exactly, and make changes easier. So once we have a top level assembly, instead of one person doing all this heavy lifting, sometimes it makes sense to use collaboration and use insight from everybody. So.
And then I know we're running short on time. The last question was, what do you consider this tool is? That's one of the questions. Is it a high-end tool or a casual simulation tool? Can you just elaborate on that for a minute before we drop off?
Yeah, sure. So NXCAE or Simcenter is a high-end analysis tool. It has the ability to run multiple solvers. So the common one here is using NX Nastran, but it has capability to pre and post all the high-end solvers. So if you are running some programs such as LS Dyna, SAMCEFT, LMS, etc., it can pre and post them. So it is a high-end CAE tool that can pre and post the majority of the major solvers out there.
Okay, with that said, Dan, that was the last question. We want to thank everybody's time. Again, if the folks could take a minute and go through the survey, we really appreciate it. We hope this is a beneficial tool to you guys. And we really thank you for taking the time from your busy schedule to join this seminar. With that, I will end the seminar. Thank you.